All right, so now we're moving on to the next section. Starting with number 5, some things are a little bit different. If you'll notice, neither one of the equations that they're giving us are already solved for a variable. What I mean by that is in this equation, x and y are on the same side, and in this equation, x and y are on the same side. So this goes back to the old skill we were practicing last week of being able to get a variable alone. Previously, we were just getting y alone. Now we're going to pick whether or not we want to isolate x or y, and how we're going to do that is going to be based upon which one already looks like it's really close to being alone. And so what I mean by that is, do I see anywhere in either of the equations where the coefficient of an x or a y is only 1? Well, right here, I have a y that just has an understood 1 in front of it. So it's going to be really easy to just rearrange this equation as opposed to this one, because all I need to do here is get rid of this 2x and move it to the other side, and then I'll have y equals, which is what I need. I need one variable equal to an expression or a number. Over here, I can certainly do that, but I'd have to move this 5x, divide by 3, and I'm going to get some fractions. It's just not going to be pretty. So I'm going to look at this first equation, and I'm going to try and get y by itself, and I'm going to move the 2x over, if you'll remember, because the 2x is positive and I'm trying to move the whole thing. I'm going to minus 2x from both sides, cancels over here, and I've got y equals negative 2 minus 2x. We cannot put the first negative 2 with the second one because this one has an x and the first one doesn't. So we're done. We've rearranged it. We've got a variable equals something. Now I can plug this in like we were doing with the previous examples. I can take this expression that they're saying y is equal to, put it in the opposite equation where the variable y is. So when I set up my new equation to solve, I've got 5x plus 3 times y equals negative 8. And we just found that the expression that y is equal to is negative 2 minus 2x. And now I'm going to solve for the x variable. So distribute 3 to both terms. 5x, 3 times a negative 2 is going to give us a minus 6. 3 times negative 2x is going to give us minus 6x. And that all equals negative 8. Combining like terms here, I've got 5x minus 6x. That's going to leave us with a negative x. Bring down your minus 6 equals negative 8. I need to add 6 to both sides. So I get negative x is equal to negative 2. And I've got to be careful because I can't have a negative variable. I need to get rid of that negative understood 1 out front there. Divide both sides by negative 1. And x is actually equal to a positive 2. Well, now I need to plug that variable back into one of the equations. Well, usually we do it in one of the originals, and you certainly can. I can plug this 2 in for this equation. I can plug it in for this equation. But now I want to be smart about it. This is an equivalent form of this first equation. So instead of going back to one of the originals, I can really do it in this one. I could plug it in here and find out that y is equal to negative 2 minus 2 times 2. So y is equal to negative 2 minus 4. So y is equal to negative 6. Sometimes people don't want you to do it in the new rearranged equation because they're afraid maybe you messed up here. And sometimes it's safer to go back to the originals. But honestly, if you messed up rearranging it, then you probably got the wrong answer in the first place, and it doesn't really matter. But if I wanted to plug it back into one of the originals, I certainly could. For example, if I wanted to plug it back into this one, I would have 2 times 2 plus y equals negative 2. So I'd have 4 plus y equals negative 2. When I minus 4 from both sides, I still get y is equal to negative 6. So once you have that first variable, you just need to plug it into either one of the very original equations, or you can still plug it into the one that you rearranged because it is just an equivalent version of one of the equations. So in the end here, we've got our x, we've got our y. The actual point where they intersect in parentheses is the point 2, negative 6. So it's the same process. I still need to plug something into the opposite equation based upon what they're telling us that variable is equal to, but now I have to do a little bit more work. There's nothing already isolated yet. I had to choose which one to isolate. I could have chosen to isolate x, but I was trying to make a wise choice and go for the easy target here. Let's try another one like that. If we look at number 6, it's the same way. X is not alone, y is not alone, x is not alone, y is not alone. Not yet, but I get to pick in either one of the equations. I get to choose which of the variables I want to isolate. In the first equation, there's a coefficient in front of both x and y, so that looks a little bit more difficult. In the second one, there's a coefficient of 2 in front of x, but y only has the coefficient of 1, which is what we like. That's what we want. It's a lot easier. So I'm going to choose to focus on this second equation this time. I'm going to try and get y alone because it's already close to being alone. I need to move this 2x over. So again, because 2x was positive, I'm going to minus it from both sides. And now I have a new equivalent equation that tells me that y is equal to 9 minus 2x. Since I know that y is equal to this expression now, I'm going to take that, plug it into the opposite equation where y is. So we've got 2x minus 3 times y equals negative 11. We know that y is equal to 9 minus 2x. Now we're going to solve it for our x variable by distributing the 3 first. We've got 2x, and negative 3 times 9 is going to give us a negative 27. Negative 3 times negative 2x is going to give us plus 6x equals negative 11. We're going to combine our like terms on this side. 2x plus 6x gives us 8x minus 27 equals negative 11. I need to add 27 to both sides. I've got 8x equals negative 11 plus 27 is really 27 minus 11, so that gives us 16. And when I divide by 8 on both sides, I find out that x is equal to 2. So now here I am again. I have one of these variables. I've got to go back and find the other. I know what x is equal to. I need to find out what y is equal to. I can plug it into this one, I can plug it into this one, or I can plug it into this one. Since this is already what y is equal to, I'm going to plug it into this one. Y equals 9 minus 2 times 2, so y equals 9 minus 4, so y equals 5. I could have plugged it back into either one of these up here. For example, if I wanted to do in this one because I'm crazy and I like a challenge, I would have 2 times 2 minus 3y equals negative 11. So I'd have 4 minus 3y equals negative 11. I'd minus the 4 from both sides. I'd have negative 3y equals negative 15. And when I divide both sides by negative 3, I get y is equal to a positive 5. So it works in any of these equations. You just got to go back and find out what y is equal to so that you can have your x and your y to write the actual solution that they intersect at the point 2, 5. So let's try this one, and I have a feeling that this one might be a little bit different. Again, neither one of the variables are completely isolated. The one on the right has bigger coefficients larger than 1 in front of them, so I'm probably going to avoid those if I can. Looking at the first equation, the y has a 5 in it, so the easy target this time is looking like this guy right here. I'm probably going to want to get x alone this time. And so this is kind of scary because we haven't really done a lot of this. But it's still the same concepts of using inverse operations to move away what I don't want. So if I want to get x by itself, now this is what the issue is. The 5y is on the wrong side. The 5y needs to be moved because I want x alone. So if I want to move that plus 5y, I've got to minus 5y from both sides. Cancels on this side, and I've got x equals 4 minus 5y. Now I have a variable equal to something, an expression, that I can plug in to the opposite equation. Be very careful because it's saying x is equal to this, so I need to plug it in where x is in the opposite equation. So if I set it up, I've got 3 times x plus 15y equals -1. I now know that x is equal to 4 minus 5y. So if I'm going to solve, I need to distribute the 3 first. I have 12 minus 15y plus 15y equals -1. So now when I combine like terms on the left side here, I've got -15 plus 15, and those are going to cancel out. So -15 plus 15 goes away, and all I'm left with is 12, sorry, not y, 12 equals -1. Well, we've been here before. We've seen stuff like this. When all of our variables go away and we're just left with 2 numbers, we need to decide if that's true or false. 12 equals -1. Well, no, it doesn't. That's not true. So if it is not true, you have no solutions. Well, now that we're actually talking about a system and a graph, try and remember what it means if it's no solutions. Well, on the graph, that means that these 2 lines are parallel and they're never going to intersect. So that is how you would know through substitution when you have no solutions. If this had happened and our variables canceled out and we had something like 5 equals 5, that would mean that it's a true statement, and that would be infinite solutions. And when it's infinite solutions, it means it's the same line graphed on top of itself. It comes out to really be the same equation in the end. So that was a what-if scenario. The answer to our actual number 7 is that it was false, it was no solutions, which meant it was parallel. So number 8 is the last one I want to try and work with you before you try some of your own. So we'll do this one last time. Neither one of these equations are isolated for a variable. So as I'm looking through, I'm looking for an easy target. The x has a 3, the y has a 2, this y has a 4, this x has a 1. So it's going to be a lot more simple it's going to be a lot easier to get this guy alone. So our goal is going to be to get this x alone. And in order to do that, I got to move this plus 4y. So I do the opposite, and I minus 4y from both sides. So then x is equal to 0 minus 4y. Well, do I really have to write 0 minus 4y? Honestly, no. So I'm just going to write x is equal to a -4y. It's going to make my life a little bit easier. So now I have the variables equal to something. I can take what x is actually equal to, plug it in for the opposite equation. We've got 3 times x plus 2y equals 20. Take that expression we just found, that -4y. 3 times -4y is going to give us -12y plus 2y equals 20. -12 plus 2 is going to leave us with -10y equals 20. Divide both sides by -10, and y equals -2. Again, I have one of the variables. I've got to go back and find the other. This time we have y. We need to go back and find x. We can plug it into one of these originals, but I'm trying to work smarter here. I have an equivalent equation that I can use to find out what x is equal to. So I've got x is equal to -4 times whatever y is, and we found out y is -2. So x is equal to +8. Remember that I need to write my ordered pair as x comma y, so the x value needs to go first. The point where they're intersecting is at the point 8, -2. So now I would like you to try numbers 9, 10, and 11 on your worksheet and enter your answers into the Nearpod so we can see how you did, and then we'll come back and go over the results, and you can see if you got it right, you can see how it was supposed to be worked out, and if it was wrong, you can correct any mistakes.